And I'd like to start by thanking the organizers for inviting me to deliver a talk in this beautiful environment. And I'd like to start my talk about neutrino experiments by telling you that physicists are fond of big blunders. In fact, I'd like to quote as a big blunder number one the words of an unknown physicist who was once quoted saying, "I am convinced that the LHC will not reach its performance design. It will never work properly. It's just too difficult." Fortunately, this anonymous physicist is unrecorded. And although there are witnesses to this blunder, they are good friends. So I hope that the name of that physicist will not be known. But let me just go and quote another big blunder, this one by a very well-known physicist called Sir Arthur Eddington, who found necessary to make a statement for posterity, for further generations. And so he said, "In an ordinary way, I may say that I do not believe in neutrinos. There I say that experimental physicists will not have sufficient ingenuity to make neutrinos." So this is the a chart of neutrino sources covering, as you can see, quite a few orders of magnitude, starting on the neutrinos that come all the way from the Big Bang. This we have not yet detected. But then if you carry on neutrinos produced on the Earth, on the atmosphere, on nuclear reactors, in the sun, supernovas, in the atmosphere, or by accelerators made by man, galactic and extragalactic, we have detected all of them, and in fact we have produced millions and millions of them in accelerators. So this put a scale in the sentence of Mr. Eddington. I'll come back to that later. Now with these neutrino sources, we have in fact, let me just give you this beautiful picture, seen neutrinos which cover the size of a city, of the city center. These are the famous Bert and Ernie detected by Ice Cube experiment. And this size of the detector is about the size of the center of Manhattan. So it's kind of, neutrinos can occupy quite a bit in detectors. So on this talk, I'm building up on the previous talk by Gianluigi Fogli, so I am skipping all the introduction about what the theory of neutrino is, because you already learned it. And let me just start by focusing on the important issues from the point of view of experimentalists. So what we really want to understand for neutrinos is identity, meaning a neutrino's Dirac or Majorana fermions. Then what is the mass scale? What is the mass ordering? What is the mixing? In particular, we know almost everything about the mixing, but we don't know yet whether CP symmetry is violated in the neutrino sector as it is violated in the core sector. And then we'd like to know more about the species. Now, if you look at the way you attack these problems from the experimental point of view, you will see that identity can be attacked by neutrino-less double beta decays, studying this. The mass scale is a number of possibilities. They do include direct neutrino mass measurements, neutrino cosmology, neutrino-less double beta decay, which is of course sensitive to the mass scale. The mass order here is again neutrino oscillations, basically a little bit of neutrino cosmology. Mixing is neutrino oscillations, and species is neutrino oscillations and a bit of neutrino cosmology. On this talk, I am going to focus only on two types of experiments, those on neutrino-less double beta decay and those of neutrino oscillations. Covering everything was just too large, and I hope that neutrino cosmology will be addressed in other talks. So just let me make a kind of quick sketch, as a matter of fact, of neutrino oscillation experiments, because there is another talk by Ernesto Kem where I think there will be more discussion on long baseline experiments. So the first thing I'd like to do is just to show you how you do experiments and how these experiments are connected with the detector that you have. So the first detector I like to discuss, in fact, the first experimental technique I like to discuss is Cherenkov detectors. There, you just use the simple fact that charged particles moving in water propagate faster than the light in the medium, and therefore you have a Cherenkov radiation emitted. You emit a cone of Cherenkov radiation that you can, and then you can put photosensors, in particular photomultipliers, that will intersect this cone of light. This implies a number of nice features. This is the super Kamiokande detector, and what you do is that you fully cover super Kamiokande detector with big photomultipliers. When a charged particle crosses by an electron or a muon, it will produce a cone of Cherenkov radiation. Cherenkov radiation will go into a bunch of PMTs, and then we can determine essentially everything. We can find the vertex position of this particle, we can find the number of tracks, direction of tracks, energy of tracks, and the particle type. All of this, of course, if the energy of the neutrino is not too high. When neutrinos of energies small enough interact in the detector and you are not making a big number of tracks, all things are very clear because you have essentially single tracks. When you make deep inelastic scattering at high energies, things become more complicated. It's more difficult to distinguish the number of tracks, but you still can do it. So this is a technology in which it was based, the famous super Kamiokande detector. Super Kamiokande detector and its predecessor Kamiokande observed solar neutrinos, contributed to solar neutrino, to establishing that solar neutrinos were part of these neutrino oscillations, and indeed came up with the first clear and mind-blowing evidence that neutrino oscillations are at work by looking at the background. And this is kind of interesting. Let me remind you that when Kamiokande saw atmospheric detectors, atmospheric neutrinos, they just thought, here, we are seeing a very nasty and unwelcome background to the real signal that we are trying to look for, which is proton decay. So they never found proton decay. But then they found that the background itself, the atmospheric neutrinos, were interesting because neutrinos coming from muons and neutrinos coming from electrons did not behave in the same way. So Kamiokande, and after that super Kamiokande, looking at the angular dependence of nu is and nu mu, did establish in an absolutely convincing way that you can see here the existence of atmospheric oscillations, which is one of the landmarks in the establishing that neutrinos do oscillate. So this is one experiment that by now would be essentially a classic, except that there is another, it has a new life because the T2K experiment is shooting a beam of nu mu's from the other side of Japan Island to the detector itself. So here we have a combination of two facts: a big water detector and then a powerful accelerator. This accelerator will produce nu mu's, and nu mu's will fly, and on the way to the accelerator, they will oscillate, and you will see two things. You will see disappearance of nu mu's, and then, very importantly, you will see appearance of nu is if theta 1,3 is big enough. Now, I was discussing with Gianluigi Foglia an hour ago the idea that when I was growing up at CERN, theta 1,3 was supposed to be very small, and this is the reason why we did the experiments NOMAD and OPERA and a bunch of others, because theorists told us so. Then theorists were cheating us. Theta 1,3 was not small. It turns out to be large. As a matter of fact, I think it's very large. And because it's very large, this experiment and other experiments that we'll discuss have been successful in the sense that it's large enough at about 10 degrees to produce enough oscillations so that you can observe an electron signal on the detector. There was no special reason why this should have been the case, because theta 1,3, I don't know of any theoretical reason why it shouldn't have been at 1 degree rather than 10 degrees. And in that case, life would have been much more difficult. But truth is that because theta 1,3 is very large, a discovery has been made, in fact, not by T2K, but by the experiment I will discuss in a second, but it has certainly more than been established also by T2K, which has now a theta 1,3 mixing angle at more than 7.5 sigma. Now, notice that when we do this kind of experiments on nu mu going to nu e, we are also sensitive to the possibility of CP violation. By running with neutrinos and antineutrinos, we can explore if indeed nu mu to nu e and anti-nu mu to anti-nu e oscillations behave the same. And T2K has a small but rather marginal chance of being sensitive to this effect. So even being theta 1,3 very large, the CP violation that you're trying to measure, even if there is large CP violation, is small enough that you want to go further these kind of experiments. Now, another technique that is a classical one because it's the technique that was used, as a matter of fact, by Reines and Cohen to establish the existence of nu e's in the Savannah River experiment is using liquid scintillator. So now, rather than water, you put liquid scintillator and you read everything by photomultipliers. The advantage of this technique is that you have a lower threshold and you have more light. So to some extent, you can measure very well the energy of those events. The disadvantage is that there is no directionality. So you don't know where the event was produced. You have a rough information of the vertex, and nothing else, okay? So this technology is, has been successfully used since the last 50 or 60 years. And in fact, I am selecting as an example the Dayave experiment. Dayave, to some extent, is a sign of the times. First of all, because it used one of the oldest technology to make a breakthrough discovery. It is by looking at the disappearance of nu mu's that you produce in a reactor that you establish the best measurement to date on theta 1,3. You use a combination which was in fact used to discover the nu e's, a reactor and a liquid scintillator. It's like you have not invented anything, right? To some extent, what you have invented here is, and it's kind of important when you look at the experimental life, is that you have perfected a technology that started with a detector this size to real perfection. It's interesting too because Dayave is an American-Chinese experiment which starts way later than the competition and blows the competition away, right? This experiment had started, everyone expected, we had the pioneer of the technique on Choth experiment in France, then double Choth came in, and before double Choth got the result, these guys came in on, and produced a really beautiful result, and to some extent unexpected. It would have not happened for a smaller theta 1,3, but it did. So, oops, okay. Now, yet another technique. What if, rather than using liquid scintillator or water detector, you go now solid? One possibility is that you take the Titanic, a ship the size of the Titanic. You take all the iron of that ship, and you make plates with it. Now you introspect the plates of iron with plates of liquid scintillator or scintillator bars, and you produce a segmented calorimeter. That was the Minos experiment, and the other example of this technology is the NOVA detector, which is looking for, again, nu mu to nu e oscillations. So this kind of detector, you get X and Y by the position of the cross scintillators in plates, and you get Z by the position of the scintillator itself. You stop the neutrino by putting iron, and you just flow through the track. You can magnetize this thing and then be sensitive to the charge and to the momentum. So the NOVA experiment, it's already started in 2014, and it's kind of the ultimate realization of this technology. It's a really big detector, and it's doing the same thing that T2K is doing in a slightly different way. First of all, the long baseline is different. Rather than 300 kilometers here, you have 735 kilometers. And this is interesting because you go through more Earth. And as you cross more Earth, you enhance the matter effects. And as you enhance the matter effects, you are sensitive to the possibility of discovering different mass hierarchies. So one of the good things of the process of the NOVA experiment is that it has a chance of establishing the existence of determining really the hierarchy within a few years, where a few years in this business always means 10 years, okay? So this is kind of the most, in my opinion, interesting feature of NOVA and the main difference with respect to the reason why it's kind of interesting to have NOVA at the same time than T2K. Now, another technology is what if you don't use water, don't use liquid scintillators, don't do a segmenting calorimeter, but you fill an enormous volume with liquid argon, and you really actually create a time projection chamber. The nice thing about time projection chamber is that you do reconstruct the tracks very nicely. You get the 3 dimensions, X and Y from wires, for instance, and Z from the time. Now, a liquid argon calorimeter is not only a tracker, it's also a calorimeter because you deposit all the energy in the liquid argon and you have good energy resolution, much better than in water. So, in principle, you can make a very nice imaging of your events, and this is an example. The one example of liquid argon technology is the Icarus detector, which were 600 tons running in the Gran Sasso laboratory. So 600 tons for reference is a half a kiloton, okay? We'll come back to that number later. Now, a half a kiloton is a big thing already. Again, for your reference, a half a kiloton is something of 20 meters and 10 meters long. You can see the detector there, okay? But it's only half a kiloton. This is what you can do with a liquid argon detector. You can do a real nice picture of everything coming out of the neutrino interaction. So, in principle, you can extract a lot of information from here. In practice, I am still not totally sure what you do with this information when you want to measure effectively the parameters related with oscillations. But the technology is there, and now notice that we are sitting today in 2014 in a moment in which experimentally Super Kamiokande, together with others, have established the oscillations. We have measured all the angles of the CKM matrix except for the possible phase. And the one thing that we don't know either is the mass hierarchy. So what the next generation of neutrino oscillations experiments need to do is to determine the mass hierarchy and to determine the CP violation phase if it is there. So let's go around how this thing can be done. Now, if what you want is to measure the mass hierarchy, you could try to use the fact that this information is contained in atmospheric oscillations. Now, if you're going to be sensitive to Earth matter effects in atmospheric oscillations, you really need a very big detector. So big that Super Kamiokande is just peanuts. Now, fortunately, we have a way of building a real big detector, and this is going to ice cube and super instrumenting the core of ice cube. You put more string, you make it denser, and then you make a super hyper Kamiokande by finally instrumenting the center of ice cube. I find this idea extremely attractive, and this kind of thing that is at the same time obvious and challenging. Obvious in the sense that the detector is there. Ice cube is there, the South Pole is there, all what you need to do is drill and equip it. All what you need to do may mean a number of millions, but there is no obvious breakthrough that you need to do, and you can do it quickly. Whether quickly means quickly or very quickly in this business means always 5 years. 5 years is ultra fast, faster than light. Quick is 10 years. So the one nice thing about Pingu is that you could really start, the nominal time is 2020. It is known that neutrino physicists are liars. And they always lie in anything that if you're lucky, it's less than 5 years. So it's 220, could be 225, could be still Fine. So this is one possibility to measure matter effects. Another possibility is bigger is better. So you have now the T2K experiment, and you say, okay, I have a nice accelerator, powerful enough, let me make it much more powerful. I have a big detector called Super Kamiokande, let me make a detector which is about 10 times bigger. So by simply using the bigger is better technology, you can build an experiment that could be sensitive in the very same way that T2K is sensitive to the combination of matter effects and CP violation. Now, because here you are only going through 300 kilometers of Earth, you are not very sensitive, as a matter of fact, to the hierarchy. You are more sensitive to CP violation. So this is one of the alternatives that you have. And this is the hyper Kamiokande idea. Certainly, it won't start in less than 10 years, and it won't run for less than another 10. So please take into account this case that we are talking about. The alternative to hyper Kamiokande is to use another kind of long baseline experiment. So again, depending on who you talk to, if you talk to the Fermilab people, they say, okay, LVNE, meaning I will build a neutrino experiment at Fermilab, and I will send it through a few thousand kilometers to a very large detector, which in this case is chosen to be a liquid argon detector. If you talk to other people in Europe, they will tell you, oh no, the thing to do is LVNO, meaning they will take a neutrino beam at CERN and will throw it through a few thousand kilometers to another liquid argon detector. So the field is not very imaginative, I would say, in the sense that two bunches of people want to do exactly the same thing. One thing I can guarantee you, there will be only one, like there will be LVNE or LVNO, but not both. Both of them propose basically the same idea. There's a difference with hyper Kamiokande. You run through many kilometers of Earth, so you are very sensitive now to mass effects, therefore to hierarchy. And in my opinion, there is something still to be understood, is that the technology that is proposed is liquid argon. But liquid argon at the scale of 50 kilotons. And remember that all what we have now, the technology has been understood, more or less, at the level of half a kiloton. Icarus is half a kiloton. You want to jump to 50 kilotons, 2 orders of magnitude in detector scale. There is a golden rule in experimental physics, and in particular in experimental neutrino physics, which is 1 order of magnitude at a time. If you jump 2 orders of magnitude, you risk to extrapolate a little bit too far. And to me, this is one of the, I wouldn't say criticism, but one of the sources of my own skepticism to both LBNE and MBNO. It's talking about an extremely challenging technology of detectors. Now, physicists are known for making blunder statements, so I will refrain myself from making another one. These are the prospects to measure the neutrino mass ordering, meaning mass hierarchy. You can see that the chances, this is number of sigmas, so the chances of nova and T2K, which are basically nova, are not totally negligible. There is a chance here, which can be improved very much by Pingu and Juno, which is like a large version of Diab. So this is kind of attractive in the sense that it can be sort of a discovery. It's only for sigma, but if you want to wait for here, it's much longer, and it's only 1 extra sigma. So you can see a number of features here. You can see that the times are long, and that the discovery sigmas are not very large. I would say that what we are seeing here is something called the law of diminishing returns. Neutrino oscillation physics has been so far extremely successful, and we have measured rather quickly all the parameters of the PMNS matrix. There is only 2 things missing, but measuring these 2 missing things is going to take quite a bit of an effort. And it's even more obvious when you look at the CP violation fraction that you can measure. This is a kind of difficult to read plot. It tells you how much fraction of CP you read, you measure with so much error. These are the current experiment. It says that after a little while, you don't measure CP violation. You just don't cover the full thing. And as you go here, you start to see that all these experiments do cover stuff. But notice that all these experiments are basically propaganda plots, meaning you put a number of assumptions in your Monte Carlo and you get a number of results. Now, even in the case of propaganda plots, you can see that in order to really cover CP violation properly, you really need to do these very big experiments, which cost a lot of money, a lot of time, a lot of effort, and which deliver one number, which is CP violation phase. So again, the law of diminishing returns is at play. These are measurements that are doable, but they are difficult. And this is one of the things I like to stress in particular in these talks. This is an effort. We are talking about an experimental program that will take no less than 20 years, probably much longer than that. All right, so now let me switch to the other side, to the identity of neutrinos, and move to a neutrinoless double beta decays. And what I'm going to do here again is I'm not going to try to cover anything or be exhaustive, just to give you a selection of ideas, of experiments, and a kind of a road to the future. So double beta decay, to start with, is a sort of respectable process, second-order process in the standard model, but measured in a number of isotopes, it's known to exist. The only remarkable thing about this thing is that it's very long. It takes typically 10 to the 19 years to happen, right? So it has been observed, because 10 to the 19 is long, but not that very long, compared with the Avogadro number. So if you put just a few kilograms of any isotope and you go underground, you can measure this mode, and it has been measured for all relevant isotopes. What is interesting is that if neutrinos are Majorana particles, then you have the alternative diagram. This is the simplest diagram that you can have. You can have many others, but all of them imply Majorana neutrinos. And this diagram will result in a neutrinoless double beta decay. In this case, you will only emit 2 electrons and no neutrinos. Now, of course, on this diagram, you have to understand that because what you have here circulating is a nu E, and a nu E is a superposition of mass eigenstates, then you have to fill in the whole PM&S matrix. And then you end up with this famous diagram. So this diagram, it contains the mass of the lightest neutrino against what we call the effective double beta mass. And the effective double beta mass is nothing but the coherent sum of this probability matrix, because of course you have to circulate all the neutrino flavor species through this diagram. So the point is that if you look at this diagram, the important thing to notice is that you want to discover the existence of neutrinoless double beta decay, and this existence depends on the mass, on this effective mass, typically, and it depends on the lightest mass. So this turns out you have different diagrams depending whether you have inverted ordering or normal ordering. So if you have inverted ordering, you can explore maybe, you see, you are able to explore 2 neutrino masses which are of the order of 20 milli-electron volts. Then basically somebody comes now and says, okay, in Pingu, I have done a measurement, and the inverse hierarchy is the one that has been chosen by nature. Then you know that if you are able to explore up to neutrino masses of 20 milli-electron volts, and the neutrino is a Majorana particle, then you are done. You are going to make a discovery. Now, if Pingu comes and says, no, unfortunately the mass is normal, then you're in trouble. Because first of all, you will need to keep exploring down, and second, there are holes here that you could not make a discovery and say, okay, no discovery, and I cannot say anything. So these kind of experiments are only kind of realistic in the event that the mass is inverted. You need to be lucky here. If the mass is direct, things become much more difficult. It's not guaranteed that you're not going to be successful in the sense that the mass could be, we could have normal ordering and still be here. We don't know. Okay? So let me discuss then experimental challenges. And experimental challenges in the case of double beta decay, one is tempted to say that it's more or less like looking for a needle in a high stack. As a matter of fact, I hope I can convince you that it's much more difficult than that. But I'll come to that in a second. First of all, let me explain how you measure neutrino less double beta decay in an ideal experiment. In an ideal experiment, it's kind of easy because you only have 2 electrons and no neutrinos on the process. So this is the 2 neutrino mode, okay? And this is your 0 neutrino mode, which is totally separated from the 2 neutrino mode because your detector is perfect. So all what you do is you count a few events here and then you're done, okay? Now, once you measure the period of the process, all what you need to do is to obtain the square of the mass of the effective mass, which is proportional to the inverse of the period. Notice this square. This square is the second reason why these experiments are very difficult. It means that experimentally what you measure is the period. So if you have no background, and you want to reduce your period by a factor of 10, it means that you run 10 times longer, yes? Or put 10 times more mass in the absence of backgrounds. But then you only improve your effective mass by a factor of 3, because you need to take the square root. Now, if you have backgrounds, you need to subtract the backgrounds. So you only improve like the square root of your exposure, but then you only improve like the 4th power when it comes to the physical parameter. So this is telling you that making these experiments are extremely hard when you go from ideal detectors to realistic detectors. But even with this, if you just ask yourself, how do I measure the period? Well, the period is simply you just run for a while, and then you get the period from known numbers. But if you do the calculation, you ask yourself, I like to explore a lifetime of the order of 10 to the 27 years. We'll see why 10 to the 27. You end up that you're going to need a ton of material, a ton of isotope, even if you have a perfect experiment. So please understand that the problem is difficult, okay? You need to pass from period to effective neutrino mass. So you need to multiply this period that you obtain in your experiment by something called a phase space. The phase space, the electrons have to come out, which tends to be democratic. It's a number. It's a little bit lower for one of the favorite experiments, which is the germanium. It's a bit higher for neodymium, which is a nice isotope, but very difficult from the experimental point of view. The problem is not there. The problem is here. This is called the nuclear matrix element. And the nuclear matrix element is one of the real big uncertainties that we have in this business. What you have here is a map, which I have no time to discuss, with all the different tribes of people who compute the nuclear matrix elements. So from the so-called shell model to the so-called EDF is passing for all these models. Every one of these models have their defenders and their retractors, and as an experimentalist, I will not dare into this very wild territory. But what you should understand is that if every model is about as respectable as the other one, there is a factor 3 uncertainty in them. But a factor 3 squared is a factor 10. So this introduces a big problem, as we will see in a second. So let me come back to experiment issues. Why neutrino-less double beta decays are difficult? The reason is that Earth is a very radioactive planet. There is about 3 grams of uranium and 9 grams of thorium-232 per ton of rock around us. And this implies, take into account, this implies that you are totally surrounded by radioactive material. And the lifetime of these guys, for instance, the intrinsic activities is at the order of becquerel, tens of becquerel, and the lifetimes are the order of 10 to the 9 years, which you want to compare with 10 to the 26 or 10 to the 27 of your process. So there are 15 or 16 orders of magnitude between signal and background. So in fact, it's much more difficult to find a neutrino-less double beta interaction in between the background than a needle in a high stack. It's about as difficult as finding a grain of sand in a beach. Okay? A typical beach, has typically 10 to the 15 sign of grams. So there is, however, things that are nicer. For instance, we have a nice signature. If we could build a detector with absolutely zero resolution, so resolution perfect, the experimental issues would be negligible. You would simply count of the events that are exactly in the endpoint of the distribution. The sum of the kinetic energy of the two electrons are always the same. The problem comes about when this is not exactly spike, but there is a little Gaussian, and the backgrounds come in. So what you would like to do, in addition of measuring the energy, what you would like to do is to have some extra handle, some extra information that tells you that what you have there is 2 electrons and not 3 photons piling up together. So one very nice feature is if you are able to reconstruct the 2 tracks, of course. This is an extra handle, as we will see is possible. So let me insist on what I said before. When you compute yourself what the signal is something proportional to the total mass of your detector and the time that you are running. But your background is also proportional to the total mass of your detector, the time you are running, the resolution in energy. The more resolution that you have, the more background piles into your region, and the specific background rate. That means the number of background counts per unit of mass. So when you ask yourself how well you progress on the period, it comes out that there is a square root that comes from background subtraction that is proportional to the exposure and inversely proportional to the resolution in the background. This means that you can do one of 2 things. You can go very high here, or you can go very low in this product, or you can try to go in between. But there is a golden law on this experiment that you have to respect. Suppose that you have an experiment of 100 kilograms, and now you want to build another one of 1 ton. Can you do that like this? Well, if you build the experiment, you pass from 100 kilograms to 1 ton, you just increase this by a factor 10. But you do not decrease this by a factor 10. You're winning nothing, basically. Because the square root of 10 here is 3. And the square root of 3, because m beta beta is the square root of the period, is a very small number. So the golden rule says the following. Every time that you propose to increase the mass of your detector by a factor 10, go ahead and improve your technology so that you decrease the product of your resolution and your background also by a factor 10. Okay? And then you improve a factor 3 in mass. All right. So who's trying to do business in this field? Basically, the field is focusing in 3 kind of approaches, and I am only describing, there are other possibilities, and there are many other experiments. I am focusing only on experiments which are believed to be capable of extrapolating to ton or more. So the experiments are the following. You can just go and build a germanium calorimeter with a little block like this that you can see here. Oh, sorry. So this little block is this size. It weighs about 1 kilogram, okay? You can put 30 of them together, and then you have a germanium experiment. Why is these are germanium diodes, why are these guys interesting? Because the energy resolution is incredible. The energy resolution is a few keV, so they are as close as we can get to a perfect energy resolution detector. Now, the problem with these guys, you can argue, is okay, but you need to put many of them. So if I need to make 1 kilogram, it's 1 block. But if I need 1,000 kilograms, I need 1,000 blocks. Every block with their electronics. Every block needs to be baby seated. And you do not have economy of scale. That means that the ratio of background to signal stays constant because you just duplicate the number of modules. So another possibility would be to say, okay, let me now go ahead and make a very big volume. And this very big volume, I will fill with some interesting isotope. For instance, I can do a big volume of liquid scintillator. I described the technology of liquid scintillator. Liquid scintillators have been used for neutrino oscillations experiments. For example, the justly famous Camland experiment, right? I have liquid scintillators. What about dissolving xenon in liquid scintillator? Now, of course, do I have resolution now? No resolution. liquid scintillators have resolution of 10%, and germanium detectors have resolution of 0.1%. So calorimeters are doing something which is almost blasphemous. I am giving up on resolution. But they are huge, so they can put a lot of mass, and they are self-shielding. The liquid scintillator shields you from the background, so they reduce B. Remember, what counts is delta E times B. So if delta E is very small, but B is slightly large, or if delta E is very large and B is very small, you're okay. So this is the blasphemous approach of Camlanzen and Snowplus, both of them very successful liquid scintillating detectors, which are now claiming they can be in this business. Third approach, you can build a TPC, a time projection chamber, which is a nice approach because you can reconstruct the 3D position of the particles. If you make it with liquid xenon, you will get very nice localization of the particles. Same technology that you're using in dark matter. So very attractive. This is the EXO experiment. If you make it with high pressure xenon gas, furthermore, you can really measure the tracks of the particles. And this is the approach of the next experiment. So Gerda, containing about 30 such crystals, 26 crystals, has already operated. You can see here what I mean with resolution. This is the point where they look like, and the resolution is just a few keV. So this kind of experiment is totally capable of measuring the background with high precision from the data themselves. They just go, they have so much resolution that if I'm looking here, I'm just moving here, I measure the backgrounds, I move here, I measure the backgrounds, and extrapolate, right? They have got a very pretty result, which is negative, and from this negative result, we can induce a limit. The next experiment, which has also taken data successfully, has no resolution. Look at this, 2.2 MeV to 3 MeV. And what do you have here? Do you have a peak? You don't have a peak, you have like a hill. So instead, curiously enough, the limit, the sensitivity that these guys get is the same than Gerda. Why? Because they compensate less resolution with better control of backgrounds, relative backgrounds, and more mass. Now, still, the third approach, which is a xenon TPC, in this case liquid xenon TPC, with the EXO detector, gets, guess what? The same result. They are in between. Resolution is better, 4%, but not as good as, better than the liquid scintillator, but not as good as the germanium calorimeters. Background is okay, same result. Everyone gets 10 to the 25 years limit. Okay, now, you want to improve on that, and there are other guys who want to do differently. The core experiment wants to use tellurium. So the idea here is the same that Gerda, high resolution experiment, but now they use tellurium, which you can display in natural tellurium has 30% of the interesting isotope. So you can put more mass. So they basically want to do a Gerda version with much more mass. Snowplus is Camlanzen, but rather than dissolving xenon, I use tellurium. And then there is an experiment which I will describe with a couple more of transparencies for obvious reason, which is the experiment I'm working in, which says, okay, let's do a xenon TPC. But now it's gas at high pressure. If it is gas at high pressure, there are two things that are nice. First of all, the resolution is good. In EXO, the resolution is at best 3.6%. In a high-pressure CPC, typically the resolution is 0.5%. So you improve on resolution. The second thing is that you see actually, so this is the experimental setup, the prototype, which with the results I'm describing have been justified. So here you can see, first of all, the resolution. This is the resolution, the best resolution we have measured so far is 0.5% with prototypes. The second thing nice about a high-pressure xenon TPC is that you actually see the two electrons. And when you see the two electrons, you can distinguish between two electrons. These guys is, as you could, we were saying this morning in Italian, a traccione rather than a track, big track. But you can tell between two electrons and a single electron, and it gives you a discrimination factor. Fine. So this is the next experiment. you put silicon PMs here to make tracks, you put photomultipliers to read the light and to measure the energy. This is the first phase of the experiment, which is the same thing to scale 1/2, and this is not drawings, but the actual experiment, which is right now being assembled and going into the Canfranc underground laboratory. If you put all the experiments together, the interesting fact is to realize, as I told you, that what counts is the ratio between this number and this product. So everyone tries to optimize something slightly different. See, these guys have very low resolution, but the background rate is slightly higher and the mass is not so high. While these guys in the other extreme of the equation, they have a very small background rate, although the resolution is very high. And the TPCs are in between. When you try to put everything together, you end up with this kind of sensitivity curves. Please focus on this one. This is in terms of number of years, which tells you that everybody, to get some decent sensitivity, needs to run for a long time, all right? And when you look at the curves, about everyone gets about the same place. Why am I saying same place? Because the number here are between 60 and 100 milli-electron volts, but this is only for a given specific nuclear matrix element. And if we look at where we are, 60 to 100 is this region. So all the experiments that are actually in the 100 region, they will never reach the hierarchy. And this is, of course, not counting the fact that nuclear matrix elements introduce a big uncertainty, okay? So this is one issue that we need to deal with. So in 2 minutes, how we go to explore the inverse hierarchy. The only way that you have is to put more mass, to get better resolution, to reduce the background. Everyone seems to have an idea how to do that. So basically, the TPCs think they can go to masses on the scale of the ton. They can reduce the background rate by a factor of 5 to 10 by improving the detector. The curious thing is that you could imagine that the diodes or the towers of tellurium could not do that, but they also think they can go and do the same thing. Same thing for the big supercalorimeters. Now, if you believe these extrapolations, something interesting happens, is that you can indeed cover the inverse hierarchy by going to masses on the scale of the ton, okay? And by going to background factors which are 10 times better than today. But if you really want to cover for all the nuclear matrix elements, the inverse hierarchy, you need a breakthrough. You need to reduce the background rate to basically negligible, that you can do with techniques like barium tagging that I have not the time to discuss. But the important thing is to realize that you really need a breakthrough. This, to conclude, is at the same time a great scientific opportunity, a great challenge and a great scientific opportunity for new underground labs around the world, maybe in this very same continent. So to conclude, there is a formula for the universe, which I like to describe here. It's a very simple formula. You take Majorana neutrinos, you take CP violation, here is CP violation, and then you get the universe, right? Here, the universe. So if this formula works, then I like to conclude by telling dear Sir Arthur that we have observed millions of neutrinos in all energy scales, from suns, supernovas, accelerators, atmosphere, the galaxy, and beyond. We have learned a lot of things about them, and maybe the neutrinos Mr. didn't believe in are the reasons why we are here. Thank you very much.
Questions?
I want to ask about the sensitivity as a function of timing. I think you show in the transparency 56.
Let's see.
There's something, it seems that you only included the statistical error in this analysis, no?
Say again?
You only included the statistical error because all the curves, they're going
No,
down.
no.
You don't have a...
These are all the errors included. Let me see if I can get this object to behave. Maybe here. No, hold it. Let me just go to this.
Yeah.
Yes. So, no, here we when you mean statistical, the background subtraction errors are included here, okay?
No, but I expect these curves can become flat for a long time, you know, because the systematic
Well,
error dominates.
they become flat if you run longer than that. But they are not, as you become longer than that, notice that these curves are already being very hardly hit. Notice that you run for 10 years and you only improve by a factor 2. So the flattening factor is already, what you are seeing is the relative scale. But if you would ask yourself, how do I fall if I only put the statistical errors? It would fall much quicker than what you see here. So it doesn't look that they are falling that flattened just because you're seeing all of them together, but they are indeed. Okay? And it tells you that progress is not very hard. You can see here at the beginning, before you start to hit your backgrounds, the curves drop very quickly. And then you can see how they flatten over here. And everyone is flattening up there.
Yeah.
There's another thing about the table you show about the spread of the intellectual predictions for the neutrino-less double beta decay. Can you say what is the source, why the different theories give so large different numbers for the prediction of the neutrino-less double beta decay?
I didn't
In the
understand
table,
that.
you show a table about different predictions for the matrix elements.
Let me see the table. This one?
No.
The nuclear matrix element. Okay, we have nuclear matrix theories around here who can answer the question. This one?
Yeah. One point is to say why you have this spread, and if you can make some experiment to try to decrease this spread.
All right, so the spread are different models. So you can see that if you look at a given model, for instance, if you look at the shell model, the shell model itself, it predicts one low point, very low for calcium, and then, in fact, shell model tends to be rather democratic for all the predictions of all the isotopes. So the orange things, shell model says the nuclear matrix element for everybody is 2. And then EDF says the nuclear matrix element for everybody is 5. Other models jump a little bit, and they have their good reasons for that. But maybe by taking these two extremes, we can sort of identify the issue for an experimentalist, is that between a flat behavior of 2 and a flat behavior of 5, there is a 2.5 factor, right? And 2.5 factor is quite an uncertainty. Now, of course, is this an argument to make a big effort on nuclear matrix element theory and reduce that? Indeed it is. But I am not a nuclear matrix element theorist. So there is one here who can make a comment.
Thank you. So, I mean, the question now doesn't look so dramatic. I mean, the spreading has been reduced very much because the phenomena, although it is a kind of nuclear dominated by those matrix elements, you can make ratios. In those cases, you are pretty sure you are measuring the lower limits of the half-life somehow correctly. So if you take, say, germanium-76 and, say, xenon-136, where you have data, both from Gerda and from Campbell and Sen. So rather than calculating a single transition, you can make rates between those matrix elements, trying to get a kind of quenching for that. And then try to see whether the other models are following this tendency. And so far, I mean, the shell model fails because the space used for the calculation is too small. While in the case of the other theories, there is no single dominance because it's not a collective phenomenon. It's being driven by very tiny configurations of the wave functions. There is nothing like a collective phenomenon involving double beta decay. So this is our mission. So it's not that the nuclear models fail so badly, it's rather the spreading of the wave function is so large that when you pick up a contribution, it is, say, 1 or 10% of the total wave functions. Now, if you take Gerda and Campbell and Sen as good lower limits, then the actual limit for the neutrino mass, assuming the mass mechanism, is about, say, 0.25 eV, so about that. And this is the best you can say today.
So let me add a couple of comments. First, that I tend to agree with Osvaldo, by the way, but if there would be other theorists from other groups that could add other information. But one thing from the experimentalist point of view is that the uncertainty in nuclear matrix element drives you to the need of having, as he pointed correctly out, at least 3 different isotopes. Remember that everybody's doing things with tellurium, xenon, and germanium? You must, because you cannot put all your eggs in a single basket. This is a clear demonstration of that. Absolutely. Absolutely.
Okay, so let's thank the speaker again. Our next talk is from Joao dos Anjos about South American institutions collaboration with Fermilab.
Thank you.
Pasame la cinta.
Put somewhere. Or? Hello? That's okay.
Right, left,
Okay. Well, okay. I would prefer that Leon Ledman should be here to talk for us about the Fermilab collaboration. Unfortunately, he's not traveling anymore. And what I am talking just because I was a witness of this history. Then I will present the Fermilab collaboration with the Latin American institutes. Well, in the prehistory of the experimental physics in Latin America was mostly centered in cosmic ray physics. No? Then, for instance, in the Brazilian example, that was the people that came from Italy, from the Second War. They went to Brazil and they started the physics in Brazil, experimental physics in Brazil, was Gleb Vactagem. And they by the 40s, they discovered these penetrating showers. Okay? Of course, after that, in 1947, there was the pioneer discovery by Cesar Lattes, well, Powell and Occhialini. And most of the data, well, the first signal was in Pico de Midi, but most of the data was in Chalcataya in Bolivia, then with a big contribution of Cesar Lattes. Well, Lattes, he discovered twice the pion, not only in the cosmic rays, but also in the artificial production of pions with Garnet at the Berkeley in 48. Then when he came back to Brazil, he founded CBPF and he started the Brazil-Japan collaboration several years after with was proposed by Yukawa to put emulsions in Chalcataya. And, but this technique was very time-consuming, and with the accelerator, the cosmic ray physics was going down, that is, was not competitive anymore. I will not talk much more in Argentina and Mexico, but there was also a little bit of, this physics was centered in cosmic rays. In Argentina, we had these exposures of plates, no? in this mountain to try to see the effect of latitude variation with the Earth magnetic field. And after that, we have this woman, Estrella Matov, that created this group at Buenos Aires. And, well, this is more or less the same history. Of course, in Argentina, there was an important part of the nuclear physics also, but we'll not talk about. In Mexico, there was the first step with Manuel Sandoval Vallarta,
he studied also the effect of geomagnetic field on cosmic rays in collaboration with Georges Lemaitre. That was a very important physicist also. Then he has some of our Vallarta had a very important participation in the experimental physics in Mexico. But anyway, it's just to tell that the importance of cosmic rays in our countries. But then in the 82, there was a revival. That is, this technique could not go ahead because it was very time-consuming, and with the accelerators now there was this opportunity, and in Latin America was Lederman get this opportunity that Latin American countries to participate in the experiment at Fermilab. Then he started when he was Fermilab director, and he organized this first meeting in Cocoyote, okay, and in '82. And there was, well, a lot of attendees, that is not just from Latin America, but also people from Glacial, Bjork, and Richter, and Chapak, a lot of Nobel Prizes. And at that time, then Clisério Álvares decided to switch, was the first from experimental, from theoretical to experimental particle physics, and to form the UNAM group. That was the first attempt to accelerate physics. Well, the conference outcome was exactly that there was 4 other symposia and a formal program to add Latin American physics, okay? Well, the second symposium was in Rio de Janeiro, organized by Thiom and Nussensweig, and in '84, the Brazilian group joined Fermilab this experiment, 691, a charm for the production. And with Clisério Álvares was at Fermilab at the same time, is why we are celebrating the 30 years of this revival of the high energy physics in Latin America. Well, in '87, the third symposium was in CBPF, and '89 in Argentina. And each symposium induced the creation of groups in our countries. That is, in Mexico was the group of Clisério Álvares, in Brazil was a group of Santoro, Escobar, myself. In Argentina was the group that Alberto Echegoyen that went to Fermilab after. And in Colombia, they also have the group that was formed. The fifth symposium was in Cartagena. Well, it was not, Lederman did not just offer people to come to Fermilab. He also provided money, the grant of $300,000. There was an epoch that we have this problem with the funding in our countries. Then he provided this grant that was used for journal subscription, publication charges, spare parts, and later there was another 150,000. That is, you see that his vision, not just to open a Fermilab, but also to help in the difficult times people to get there. Well, this somehow in '87, Carlo Rubbia decided to follow Lederman's initiative and also invited Latin American physicists to join CERN. They were very jealous one from the other one, that is, there are both some competition. But anyway, this initiative of Lederman somehow led also the collaboration with CERN a few years after. Well, it's in Fermilab, that is, the Latin American groups have participated in several types of physics. That is, the first one was a heavy flavor, charm physics, but also light flavor physics, so in CP violation. You have here all the experiments that we participated. Collider physics after D0, and after that in neutrino physics. Then I will not enter more in detail. That is, the first experiment was the 691, was charm experiment, and was very important because it was the first successful use of silicon microchip detectors that allowed to reconstruct vertex, and was a very, that we did not invented this silicon microchip, but was the first successful use of these detectors. And we were able to reconstruct 10,000 charm events. Well, one spin-off of this experiment was this idea of parallel computing that was invented at that time at Fermilab. And this is, for instance, 1 day of data taking. You need something to carry on. And when we have developed this technique, then we use this small to put the data on these small processors. Well, this other experiment was in charm hardware production. That is, I will not enter in detail, but we saw the dependence of charm for different targets. Okay, was also one new idea was to use parallel computing instead of picking one event at a time. Using parallel computing, you pick parts of the events in several processors, and then you join all of them in just one. Well, is the thesis that is, you see that there's a lot of Latin American people that participated. This is another experiment that is, we also have a lot of theses just to show the success of the program on the year over. And here, for instance, you go to this experiment, radioactive hyperon decays. If you look to the publication, you see that the first author, most of the time, is Latin American. You see here is all the experiments, all the papers published, and you see Morelos, Albuquerque. Then you see the importance of Latin American contribution in these experiments. Well, I will not, in 791 was important because, well, I go fast, but anyway, was the first, was important this result, that is, we see this resonance modes, that is, it was F0, we measure it, and also the pi scalar resonance, the sigma and the kappa. Okay, that is our interesting results. These are the theses, I will not go around. And if you see the publications, we also, the Latin American has about 25% of the publication of all the papers, that is, were responsible for 25%. Well, focus, and here instead of 10,000, we 1 million charm particles. And well, I just go through, I have no time to see. And this experiment was important because there was a lot of collaboration with Mexico, the Brazilian-Mexican group. Is an example, a thesis of Cecilia. Well, I go pass through, but you see that there was activities in several experiments, okay? And more recently, in neutrino physics, that is, this is the Minerva, all the theses, and a lot of also Latin America was the first author of the papers. Okay, Minos, and at D0, the Brazilian group worked in the B tagging that was very useful using the top discovery. Okay, that is not directly on the top analysis, but in the bit tagging analysis. And also was the first proposal to build a part of the equipment was the forward protodetector, was an upgrade of D0, and it was built here in Brazil, that is a part of it. And this is the results of for the cross-section with this detector. I have no time to, this thesis, okay, of people. You see the number of people that was formed. Okay, then there's a summary for the Brazilian, for instance, participation. It is a lot of institutions, and the present is about 150 scientists that participate in 12 different experiments, okay? The main problem is the financing, that is long-term financing, that is the projects are approved, but it's difficult to sign a memorandum of understanding, and long-term finance is not assured. Well, from Mexico, I just go very fast. Anyway, it started with Glycerio, but first in the theory part, and then Glycerio and the Hector Mendes, Antonio Moreno, Gerardo Moreno, and these are all the experiments that were participating, and they also in collider feeders, and now in neutrino also. Then you see here the number. In Argentina, Fermilab was very important for the contribution for the choice of the site, of the decision of the site of the experiment, because Alberto Echegoyen went to Fermilab. He discussed it as a guest scientist, and then he participated in the discussion of Auger, and he came back to Argentina to find a place, to find a site. And it stayed 2 years to find the site. And finally, Auger was built in Argentina and was the most successful Latin American project ever. Then there was also participation in a collider experiment in D0, the group led by Ricardo Piegaya. And of course, now all the groups are migrating to my time is over, but just finishing. I'm migrating to CERN, but anyway, is the situation in Colombia that also started very early, okay, in this experiment, and then in D0. But at the final, that is all these first groups joined, and now they are joining CERN experiments. But that is, the groups were first formed in Fermilab. Okay, this is the contribution also from Peru that started in 2005. Okay, there are other experiments, that is the theory group, astronomy group, and the participation in this experiment is Sloan and dark energy. That is, it's just starting. It started last year. And there are also people from Latin America, okay? And now Fermilab is also going back to Latin America with this CONE experiment that we'll talk tomorrow. It's about neutrino coherent scattering, and was approved this year in this project at Fermilab, okay? And finally, people will return to come back to Fermilab because there is new activities, that is LBNE, that will start in a few years, but the tests are already the people involved is already started. In Brazil, for instance, we have 7 institutions, about 11 people, and well, they are interested in this. As a summary, that is, in the first stage, the Latin American participation was just integration with other groups with more experience. In the second stage, the responsibility for the construction and maintenance of the detector. These are examples of detectors that are well built, okay? And the same for data analysis. And conclusions in that the last 30 years, Fermilab has played a very important role in the development of high-energy fields in Latin America, and led an initiative and support made possible the creation or the recreation of the experimental high-energy groups in all our countries, okay? And led to a community of about 1,000 researchers today of this size. And also this allowed to have the good conditions for a good Latin American participation at CERN. And now the construction of neutrino facilities at Fermilab will increase again the Latin American participation in the lab. Well, thank you.
Any questions for Joao?
I already had my time, it's already, thank you.
Okay.
It's just
Well,
historical.
Let's thank him again. So the next talk is the opera experiment.
And permit me to visit this so charming country. So thanks for this opportunity. Now all is ready or not? Okay. So I will report about the opera experiment, and here the outline of the talk. The opera experiment with some detail about physics motivation, Newton detection principle, and the opera detector. Then the physics results obtained for Charmed Hadron sample, neutrino oscillations, and atmospheric muons. Opera means oscillation project with emulsion tracking apparatus. Is a long baseline experiment searching for neutrino tau appearance in a pure NUMU beam. Opera use a hybrid setup to detect the neutrino tau charged current interaction and to direct observe the tau decays. Opera aims to provide unambiguous evidence for new tau oscillation in the parameter region indicated by atmospheric neutrino data. The opera collaboration is of about 140 physics from 11 countries, with two important components from Japan and from Italy. The physics motivation is linked to some historical hints, obviously. Neutrino oscillation in the atmospheric sector has been established in 1998 in disappearance mode by Super Kamiokande and Macro. Oscillation mechanism was then confirmed by accelerator experiments in Japan and in United States, as well as by solar neutrino experiment. All these results were obtained in neutrino disappearance mode. But oscillated neutrino appearance was a missing tile in this picture. So in Europe, two experiments, Opera and Icarus, were planned in to study neutrino oscillation in appearance mode. In particular, Opera aims to provide the first direct detection of neutrino tau oscillation in appearance mode, as I said. To observe the neutrino tau appearance, Opera detects tau lepton decay. And the challenge is to distinguish the neutrino tau interaction from neutrino mu interaction. We can see in this slide the neutrino mu interaction at this vertex, and on the contrary, here is the neutrino tau interaction and the tau produced, and then with the its decay. To do this, choice, opera uses a topological selection. That is, a kink is the signal that a decay could be present. Here we see the position of the kink and the decay of the tau. The tau decay detection has two conflicting requirements: a large mass because of low cross-section, and an high granularity to select the signal and to reject the background. So our detector consists of a LED, a nuclear emulsion target, segmented into basic unit called bricks, complemented by electronic detectors. Nuclear emulsion, because they allow the 1,3D particle reconstruction, a submicron spatial resolution, and a high granularity. Electronic detectors provide the timestamp, preselect the interaction brick, and reconstruct charge and momentum. So the real brick is shown in this picture. This is the brick, and this is the wall that is an iron grid where the bricks are arranged. The total target mass is 1,250 tons, and very near the wall we can see another structure that we call target tracker. Here the target tracker, and the tasks of target tracker are trigger of the interaction, brick finding, and it initiates also muon tagging, because all these operations are impossible for the emulsion brick. So the detector, the wall detector of Opera, it consists of two identical supermodules, where is a target section and a muon spectrometer that is a dipolar magnet instrumented with RPC and drifted tubes. This detector is mounted at Gran Sasso National Laboratory, where the caverns are oriented towards CERN. And we can see the whole sea at Gran Sasso, and the Opera detector is here, and so is exposed very well to the CNGS beam. This beam, CNGS beam, is a beam of pure NUMU constructed at CERN and tuned for tau appearance at LNGS. This beam travels for 730 kilometers from CERN to LNGS, and obviously travel under Florence, Mont Blanc, and so on. The mean energy of the beam is 17 GeV, and the very important thing is that all the components are very small, but the components of this beam of neutrino tau is fully negligible. After 5 years of data taking from 2008 to 2012, we collect about 18 times 10 to 19 pot, and overall 20%, unfortunately, less than the proposal value. When opera is during the run, online analysis of electronic data is performed, and by using an algorithm for brick finding. The brick with the interaction, the selected brick, is removed from the target and exposed to cosmic ray. Emulsions are developed and sent to scanning station or laboratories. In the real measurement and analysis of this interaction is performed in the labs, is event location, decay search, and so on. So I go to the physics results, and here is a charm. Charm decay has the same topology as the tau, so is used as control sample for us. We use the same topology, the kink topology, to search the decay, and we have very good results in number and also in shape for this search. So I have so small time, so I prefer to say something about Monui oscillation. These results are already published. We found 4 events with a background of 4.6 events, so compatible with the background-only hypothesis. We set this value already cited in PDG. Now the analysis is in progress, and we have 40 new candidates observed. In the same data set, we search also for non-standard oscillation, and also this analysis is in progress. The opera collaboration foreseen to finish measurement and analysis of all bricks in the next year. And here, in the past summer, we have 7,000 located interaction, and in this sample we find 4 neutrino tau. This is the first candidate event, in decay tau in 1 hadrons with, here I report all the kinematics quantities measured by us. This is the second neutrino tau candidate, this is a decay in 3 hadrons. Very interesting, the third is a decay with muon, very clean event, very well reconstructed. And now the last event found this year, presented at first time at Boston in neutrino conference. And with these 4 events, opera states really a first observation of neutrino tau appearance. With 4 observed events, with 0.22 background events, this value of probability corresponds a 4.2 sigma significance of non-null observation. We try also a first measurement of delta m squared to 3 with the neutrino tau appearance. So large errors, but good agreement with the previous determination. Atmospheric muons is an interesting measurement because we had the measurement of the atmospheric muon charge ratio in the TEV region where no results were available. We find these results compatible with the expectation from a sample pi-k model. And in conclusion, we can summarize our results are a first observation of neutrino tau oscillation in appearance mode, 4 neutrino tau candidates, no oscillation hypothesis excluded at 4.2 sigma, first measurement of delta m squared to 3 in appearance mode, some first results about Numuno oscillation, the most accurate determination in the energy range 120 TeV for the atmospheric muon charge ratio. Now in progress are the two analysis, oscillation analysis, and some improvements in the statistical analysis. So thank you for your attention.
So questions?
So you said that a more complete analysis of goes to nu tau and nu e is underway. How much more data remains to be analyzed?
No, the run is finished.
Yeah.
But we are continuing the measurement of the bricks in the labs. How many events we can find, I don't know. Is a chance to find a neutrino tau. We hope another events of oscillation, but it's not sure.
More questions?
Okay.
Okay, so we thank the
Okay.
speaker again.
So
Thank you.
That is one of the experience of the next generation of experiments with that can achieve an unprecedented precision to do neutrino physics. And during this talk, I will try to answer for Juan José the meaning of the last letter of the acronyms of the experiment. So this is the outline of the talk, and I will first touch the open questions in neutrino physics that have been stressed during the previous talks in this morning. And then I will go through the LBNE experimental program, describing the science that the collaboration wants to pursue. And I will describe the detectors of the experiment to try to solve the questions posed by the science case. And then I'll show to you some sensitivities expected by the current, for the current experimental design. Okay, so this is a nice picture showing the interplay between different branches of the high energy and particle physics, and in a very synthetic way. And this is the arena that we'll play our game with the LBNE experiment, that it's the so-called intensity frontier. And these are some statements written in the P5 report that was lauded in 2008 about the need to go deeper in the knowledge about neutrino physics, and because this is a key element to try to find the missing pieces of the puzzle. and the essentials of the standard model. So at the time, the P5 has recommended a world-class neutrino program as a core of the US program, but I would like to say that, of course, that it's a recommendation of USA advisory panel, but same recommendations have been made by European and Asian similar panels. So this is the third time that you are hearing about these questions in this morning. And this is the main questions that we have to try to answer in the next future within the context of neutrino physics. And the first one, if there is or not CP violation in the lepton sector that can open the door for leptogenesis to explain the asymmetry of matter and antimatter that everybody knows that it's a large consequence and impact in the cosmology. And also about the neutrino spectroscopy, we have to answer the question if we have a normal hierarchy, just like in the quark sector, or inverted hierarchy. And up to now, the oscillation experiments are not able to answer this question. Do we have a maximal mixing in the neutrino sector? And if so, why? And this can address answers for the symmetries in the quark sector, in the lepton sector. And are the neutrinos, they're all antiparticles that have been discussed by Juan José very well, and the impact of if they are Majorana or Dirac particles. And moving to astrophysics, what can you learn from supernova neutrinos? Because much of the information that we can extract of the supernova dynamics can be taken from the neutrino spectrum and the time distribution of the events. And then a second, more harder question to try to answer, but we can try to do that if we can observe the supernova diffuse neutrino background from the past supernova integrated all along the history of the universe. And then more exotic questions that if neutrinos can fill up the cracks in the standard model, and about dark energy, extra dimensions, and sterile neutrinos. So this is a new version, a brand new version of the P5 report in which the recommendation for a long baseline experiment was kept from the previous document. So they still recommend that we must have a long baseline neutrino facility. Now facility stands for the fact that the Fermilab will host an international collaboration that will manage a large long baseline neutrino experiment to achieve these scientific goals. And then this is a sketch of the main concepts of the LBNE experiment and with the key points of the experimental design. There will be a very intense and wide band neutrino being produced at the proton facility at Fermilab, pointed to a far detector placed 1,300 kilometers away in the South Dakota state at the same underground laboratory that Mr. Davis ran the famous chlorine experiment for decades. And just near the production point, there will be a near detector to make precise measurements on the flux and the energy of neutrinos produced in the beam. And this is the collaboration that up to now is made of 550 members with 90 institutions distributed over 9 countries. And this is the list of the science goals of the experiment that is not a coincidence, that matches perfectly well with the recommendations of the P5 of the physics that have been cleared in the next future with neutrino experiments. And these are some figures and parameters about the LBNE. And we need a wideband neutrino beam because, as you see later in the next in a plot that I will show to you, with a wideband neutrino beam, it's possible to see structures modulated from the first and the second maximum of oscillations. And this is the power that should be achieved by the beam. And as the fire detector, we intend to build a 50 kton liquid argon time projection chamber at this level underground that stays at more or less at 4,000 meters of water equivalent, that reduces the cosmic ray background at these rates at 0.1 hertz. And the detector has 3D capability, and these 3 coordinates will be provided by this number of anode plane assemblies, and the wires wrapped around the assemblies will provide these 2 coordinates, and the position of the assemblies along the detector will provide the X coordinate to do the reconstruction of the tracks of the particle. And the signal must be very clear, because we will have a very good production of secondary particles by the ionization in the argon, and also for produced by the scintillation of the argon. And these are some figures about the near detector, that it's well designed to give us precision on the flux and energy of the neutrino being produced at Fermilab. So, to have the features of the beam that we intended to shoot for the fire detector, there is the proton improvement plan that it's approved by Fermilab, and to use the old beam lines to increase the power and intensity of the beam. So this is a sketch of the fire detector, showing to the 2 volumes and the anode planes spread all along the volume. And this is the shaft. This is the configuration of the underground site where the detector should be placed. And this is the shafts to give access for the experimental house. And there's some prototype working already run in Fermilab, where we are building a 35-ton reduced scale prototype of the time projection chamber. And for the next future, we foresee a next test in the CERN beam using elements with the size, the same size that should be placed in the fire detector. And this is some pictures about the prototype, the 35-ton prototype that it's been assembled in Fermilab. These are some pictures of the Surf Underground Research Facility, showing that we have some demonstration experiments already running for neutrinoless double beta decay, dark matter experiments. This is a picture showing how is the refurbishment of the experimental hall that gives access to the old Davis Cavern. This is a schematic view of the near detector, as I said to you, with some more complex elements to give a precise measurement of the flux and the energy of the neutrino beam. And let's move to some physics that we intend to extract from the experiment. And this is the expected neutrino spectra with no oscillations. And these are the oscillations pattern for different parameters of the mixing matrix. And this shows to you the choice for the baseline, that if you have a too much short baseline, we will not have enough sensitivity to discover the CP violation phase, and also to tell something about the mass hierarchy. If the distance is too long, the flux will be reduced, and the sensitivity for the CP violation measurements will also be reduced. So we'll have here a perfect distance to match both requirements for CP violation and mass hierarchy measurements is around 1,500 kilometers from baseline. And this is the expected simulation of the expected spectrum at the far side, showing that it's a very clear structure of the oscillation effects over the neutrino spectra, and this is the number of expected events, and with this exposure. And this is the sensitivity for mass hierarchy and CP violation, and to translate this in years with this current configuration, it's possible to achieve 4 sigma in mass hierarchy and 3 sigma for CP violation discovered in more or less 5 years of data taken. Concerning supernova detection, I have to say that liquid argon offers a good opportunity to detect electron neutrinos that it's very different from the water Cherenkov detector that is mainly sensitive to electron antineutrinos, and this can provide important information about the neutronization burst, that it's one of the first phase of the supernova, the core collapsing supernova. And just to end with the physics that can be done with the LBNE, we'll talk about the proton decay sensitivity, and the liquid argon has high efficiency for SUSY-favored decay modes, around 97%, and this is the current limit imposed by Super K, and it's possible to see that with the configuration that we are proposing, in few years we can reach a higher sensitivity, a higher limit for the proton, for the baryon violation process. So this is scheduled, showing that the construction will take at least 10 years of the experiment, and it will run a complete configuration in 10 years. And just to try to answer the question of Juan Jose, and why LBNE to LBNF? Because there is strong recommendation of the P5 people that the experiment should be managed by international collaboration. So the Fermilab will work as a facility to host this experiment that should be run by in a very fair process by international collaborators. And this is a letter to invite people to take part and to attend the first meeting, and to refound the collaboration, put all the things in the current way. So the conclusions is that we have a scientific motivation, all the ingredients to do a very rich program, experimental program, and try to answer the open questions in neutrino physics. And we are moving to a large international collaboration to manage the science and the technical aspects of the experiment. And I will invite everybody that is interested to take part of and to join us in the collaboration. I'm available to give some further details and to discuss with you. Okay, thanks very much.
Okay, questions?
Thank you for this nice overview of LB&E. I have a quick question. So you talked about how for LB&E, the baseline is more or less optimized for mass hierarchy and also to cover
Yes.
a good range of CP violation. If I'm not mistaken, LBNO has a different
It's 2,000 kilometers.
baseline.
Yeah.
So what does that allow to do better?
So I don't have here some, but I can show you some plots about that. There is some difference also because the proposal for LBNO, the beam has a different energy around 80 GeV. And there are some simulations that both people, that's a joint effort, a common effort between LBNI people and LBNO people to try to solve. And they run many of simulations. And the answer is the baseline of, with the energy of LBNO can increase slightly the sensitivity for the mass, the CP violation mass hierarchy determination. It's a little bit more sensitive, but not large enough to justify the construction of 2 experiments in 2 different places in the world. And moreover, there will be people from LBNO made a visit 1 month ago at the SURF laboratory and to check because the laboratory is already running, so the cost to implement the new experimental hall can be dramatically reduced if you make a comparison with a build of a new laboratory of 2,000 kilometers far away from the beam. So if you take, summing up the decision to use this 1,300 kilometers for baseline is more or less take it away.
Okay, well, let's thank Ernesto again. So we reconvene at 2:30 sharp. We're going to show where is the place for the reception tonight. It's on the board already, okay? It's in Parque Explora, just a little bit further away from where we have lunch. Okay, thank you.